So I was thanking the organizers and for the opportunity and also for being in this set of good talks this morning, which everyone who has talked here is a friend, and they are such good friends that they have pushed my talk to start when I should finish. So, so I'm going to talk about all of these things, but very briefly. I don't want to be very technical. I just want to tell you what we were looking for and what the result is. And kind of every of the things that they have been mentioning this morning are in this title. So Anna mentioned observational prospects for cosmic strings, and she said that they can be gravitational things or they can be radiation things. So I have both things in the title. So I'm going in my talk I kind of blend those things together. So this is work done in collaboration with a student in Bilbao, Jon Urrestilla, and a postdoc, Irene Sendra. So the overview of what I'm going to say is, we have seen this picture many times this morning. So this is the CMB power spectrum. And there is something like a cosmological standard model that fits this data very well. And there are 6 parameters that you have to fit to do this. And as Levon also said, there is no need for cosmic strings to fit this data, but there is room for cosmic strings. So the same way that there is room for cosmic strings, people look for other things. So for example, people have been playing with this NF, which I will define in the next slide, which is the effective number of neutrinos. And they have found that there is no need for anything else, but there is room for something else. So depending on your point of view, there is something there. And depending on your point of view, there can be something else there. So the question is, if there is something else apart from these 3 neutrinos, what is it? So it can be some other relativistic species, and that can be also gravitational waves. So maybe we have something more than 3 neutrinos. That something more can be gravitational waves. And if it is gravitational waves, where do the gravitational waves come from? So as we have heard this morning, gravitational waves come from cosmic strings. So if I play this game of leaving the parameter NF free, I get a number that tells me how much NF I can have. That NF tells me how many gravitational waves I can have, and that would tell me what is the G mu of the strings that would produce that NF. So in this work, what we did is study what is the correlation or the interplay between this NF and G mu. So let me define what NF is. So the peaks that we have seen in the previous slide depend on the contents of the universe and the radiation content of the universe. So mainly it's photons, but we have something else. So the something else is neutrinos and maybe some extra components. And all these neutrinos and extra components are put into this NF parameter. So this is the definition of NF. If we only have 3 neutrinos, this NF is roughly 3. If we have other things, this NF will go up. And different CMB experiments, combining with other type of data, have found that NF can be or is 4.5 or 3.8. If you take into account the errors, both these numbers are okay with 3, so there is no need for anything, but there is room for something. So this is what I just said. So NF is not necessarily only neutrinos, it can be something else. And the something else that can be, it's gravitational waves. So this is the cosmic gravitational wave background. And there is a way of relating, this is the density of gravitational waves, to this NF. So if you give me the spectrum of gravitational waves, I can integrate that and tell you to what NF they correspond to. And the next question is, if that's the case, where do the NF come from? And they can come from cosmic strings. So we have this very ugly looking parameter, which I don't know why I chose to call it like that. So it's the number, the effective number that would come for cosmic strings through the gravitational wave emission of these cosmic strings. So instead of saying NCSGW all the time, we will say N string, but that's what I mean. So depending where you give this talk, you have to start telling people what the cosmic string is and how they are formed and all these things. Not here, so we all know what the cosmic string is. So I have something like that, which produces gravitational waves, and those gravitational waves fit into the NF. So we've heard this morning cosmic strings contribute to the CMB, and this is a difficult calculation. There are different ways of doing this, and for my standard, comparing to what comes next, more or less we agree. There is a factor of 2, which I don't really care right now. So we more or less understand what happens in the CMB point. Also, cosmic strings create a cosmic gravitational wave background, and this is even more difficult to study. It is not at all understood, and depends on things like loop distribution, the evolution of the loops, the decay of the loops, and all these things are under discussion. So there is a big question mark here of, if I have a network of cosmic strings, what is the gravitational wave background that they create? So this is, that's how we say that we are starting to walk towards this direction, but we don't really believe the next step that I'm going to give. So there is a paper by Olmez et al., and they analyze this for Nambu type strings, and they say, okay, if I have loops that are smaller than the horizon, there is a way of relating the G mu of the strings with the end strings. So if I have strings of this size with this tension, they give me this NF. Or if I have loops that are bigger than the horizon of a certain tension, they give me some other NF. So I have a recipe, if you want, to go from string tension to the effective number in cosmic strings. So there was a paper prior to this paper who took this path and said, okay, I have the CMB, I fit the CMB leaving NF free. This gives me the possibility of having gravitational waves, and these gravitational waves, through this formula, can be translated into G mu. So then I get an upper bound in G mu. But this is not totally consistent, because we just started saying that cosmic strings also contribute to the CMB. So I have to put the cosmic strings from the very beginning into this analysis and say, I have CMB and strings. Let's see if putting the strings here actually changes how much NF I can have, and do the whole process again. So this is what we did. We started analyzing the CMB with the strings including, and see what the NF looks like. So this is what I want to do. The results are lots of plots and lots of tables that I will only show 2, because I want you to have the flavor of what is going on. You can ask me later on. But this is basically the idea. We have seen this picture maybe 4 times this morning. So CMB plus strings. So what we did is CMB plus strings plus maybe changing NF. So this is what I put into the computer. I feed the data. I have my usual 6 parameters plus NF plus strings, and I use cosmological data. I use CMB data, WMAP and SPT, and I use non-CMB data, so the measurement of the Hubble constants on baryon acoustic oscillations, and study how NF and G play with each other. So this is one of the results. So these are likelihood contour plots. This F10 is how many strings I can have, and here we have NF. So we see that there is a correlation between these 2 things. So we have to be careful when we include these 2 things, because they talk to each other, and they do create correlations. And actually, it's even more complicated than we expected, because depending on the data that we're actually using, something can be an anti-correlation or a correlation. So it's difficult to do this well, so you have to be careful and do it slowly. So first result is that they are correlated. They talk to each other and something's going on. The second, if you want, result is that even though you can have the case that they both push each other up, we still don't get a lot of strings. We always get a small fraction of strings. And if you want to be optimistic, there is one case where we found a 2 sigma hint for strings, but nevertheless, there is a small fraction all the time. And these are numbers that come from these calculations, which is a lot of information here that I don't want you to go into. I just want you to show the numbers that I'm talking about. So this F10 is the fraction of strings that I can have. So you see that it's 0.04, 0.04, 0.07. These are the mean values, the 0.04s. And the number in parentheses that says less than, it's like an upper bound, a 95% upper bound. So strings have to be less than that, less than that, and less than that. So typical numbers are small. And then I have here this NCSGW. So this is, if I allow for strings to be in this analysis, these strings create an extra number of neutrino, in quotes, a relativistic contribution. And if those strings are smaller than the horizon size or larger than the horizon size, I can actually translate this G mu into what that NF number is. And you see that for small loops, the numbers are relatively small. For large loops, larger than the horizon size, the numbers are relatively large. So this N equals 2.8 has to be compared with the NF, which is 6. So the numbers are very big. So I think I have that written here. So these two numbers are the translation that I just showed you going from string tension to gravitational waves. So then there is these two last lines, which is I have left number of neutrinos free. I know that I have at least 3 neutrinos. So that's this minus 3 here. And I know that because I have put the strings into the soup, the strings also create NF. So this is this here. So this subtraction says, I need this amount of NF to fit the data. 3 of that comes from neutrinos. Another amount of that comes from strings. Do I still need something else or not? Or I am okay with this, only these ingredients. So you see that the errors are very big. But one of the things that you can see if you look at the numbers slowly is that to 2 sigma, almost all cases are okay with having only strings. So if I have a model that has NF free and has cosmic strings, the gravitational radiation that those strings create is exactly the one I need to compensate for the extra NF that I need. So cosmic strings can explain the NF needed. Another thing that you note here is that sometimes the numbers are negative. So a negative number means that the extra NF that the data tells me that they want is less than what the 3 neutrinos would give and the corresponding strings would give. So if this number is negative, what this number is telling me that the gravitational radiation that comes from the strings is too big. It's too big for what the data wants. So this could be another more stringent consistency check. So we not only move the TT, the power spectrum, from the CMB, but we also create too many gravitational radiations from the strings. So those are the conclusions. First of all, there is a correlation between these two things. So if I add strings to the CMB, that adding the strings to the CMB changes what the value on F is. The behavior is interesting and complicated because you can have correlation or anti-correlation. And then if I have cosmic strings present, they create gravitational waves, and those create NF. So I can have a situation where the strings are enough to account for everything I need in my model, or I can have situations where the strings are too much, and this is another way of constraining the models. Caveats. So this is everything. It's a caveat, it's a work in progress, and it's a wish list. So first thing we said, the CMB for strings is very difficult. So I am part of the group who does abelian Higgs field theory simulations. So we went from 512 cubed in 2003 to 1024 cubed in 2010, and now we are in 4096 cubed in 2012. So Mark Heimers talked about this a bit. So we are using 32K processors to do something like this. And this is a picture of only one slice, because if I plot everything, you cannot see anything. So the boxes are getting much bigger. The boxes are getting much bigger, and we have lots of stuff. So we hope we are start to please the people who do Nambugoto to say we are doing big things now. So maybe we can get something closer to reality. So this is one direction in which we can improve what I have just said. Maybe we can get a better prediction to the CMB from the strings. Difficult, but we are working in that direction. Even more difficult is what is the gravitational wave the gravitational waves from strings. There are some works in Nambu-Goto type strings in this direction, and this is actually what we used to do this work. And now we have started to think of this also in field theory. There were some previous work by Dufault and Figueroa, and now we are also, this is a bit of advertisement of something that hopefully will come out this month. So we have taken our simulations. So we have, in this case, it's a network of global defects. Eventually, we want to do cosmic string. So we put the global defects into the box. We simulate them. And the energy momentum tensor of these defects is fed into this equation, so the transverse traceless part of it, to actually calculate what is the transverse traceless part of the metric perturbation of this. And from here, hopefully, get what the gravitational wave background of this model would be. So this is, in all this game of CMB, there is the field theoretical point of view, the Nambu-Goto point of view. In gravitational wave, there was the Nambu-Goto point of view, but there was not the field theoretical point of view. So this is starting to go in that direction also. Hopefully we will meet at some point. And the result of this is that if I have a scaling network of things, whatever the things are, what I obtain is a scale invariant spectrum of gravitational wave backgrounds of this form. And there is also one number, which is this FU, that has to be read from the simulations. And we will give some of these numbers in the paper that hopefully will come out. More things which are more into the wish list than in the work in progress. We will have Planck data hopefully soon. Can we say anything from Planck data? Will Planck data will be able to break the degeneracy between NF and G mu? We haven't included any of the the primordial gravitational waves, so the famous R, tensor to scalar ratio. If I include R, what happens? Are there even more degeneracies with the strings and F? We haven't said anything about polarization. Levon talked about this. Polarization should be also there and taken into account. And everything that I have said so far is for vanilla abelian Higgs strings. What happens if I have extra dimensions, if I have cosmic superstrings and things like that. So this is all I wanted to say. So, questions on lunch?
Sorry, before we have any questions for you, I have to announce that there have been a few changes in the schedule for this afternoon, and you can see them online or on a paper outside. Okay, let's take some questions for you. Go on.
And then we're starting at the same time in the afternoon?
Yeah, we're starting at 12:30. So we
12:30.
Sorry, 1:30.
1:30.
Question. I actually had a question about N effective. That constraint doesn't depend on any spectrum for the energy density in gravitational waves, does it?
And in cosmic string gravitational wave.
Yeah.
So when we take it, it's the gravitational wave spectrum is flat. So we integrate between two numbers, but what we are integrating is a flat.
Any other questions? Okay, if not, let's go get some food.